here programs on a regular basis? So kind of like, okay, so like 30% of the crowd. Who here has ever coded in Mathematica? 1, 2, is there a 3 in the back there? No? No, okay, so 2, okay. And who here has ever used Wolfram Alpha? That statistic changes with age group. Like if you ask any college student today, 100% or 95% raise their hands. Anyone who studied math. Here has ever used Siri? Come on, people. It's the age of the voice control. You got to move faster. So, okay, that's good to know because it kind of depends how I'll structure the talk and what I'll extend on. There's kind of a portion of this talk that's a lot about terms and workflows, and then there's a larger portion that involves actual coding and doing some data science, and I'll try to reduce that as interest. So, my name is Eraz Kaminski. I work for Wolfram Research. We're the company that makes Mathematica, Wolfram Alpha, a lot of other systems worldwide that are rebranded. I work in our Wolfram Technology group under the Technical Services group, which is our technical consulting group. And we do projects for a wide variety of clients worldwide. And I'm kind of here trying to talk about our approach to data science and the type of work we do for clients in that world. We call it Multiparadigm data science, and we're gonna go and dive into what that is exactly. So just a short outline of the talk. We're going to talk about what is data science, and then we're going to talk about what is multi-paradigm data science. And it's more of a formulation of data science than it is a specific topic. It's about a way to structure your data science pipeline to make it effective. Then we'll have a short example of a data science workflow, which I'll kind of code as we go. And then we'll have a more longer demo and explanation about data science pipelines and how to build a long-term flexible pipeline for your business, or how to arrange to have other people build that for you with the right ideas in mind. So what will you get out of this workshop? First of all, this is actually an 8-hour course. We've summarized to 45 minutes, so that was kind of challenging. That outlines our ideas of data science. So the first thing is you're going to learn about multi-paradigm data science. You're going to learn how to build a data science pipeline with less of a coding crowd. We'll try and less focus on how to build it and unlike what it actually is. And you'll learn about applying machine learning statistics, importing, website scraping, database scraping, visualizing all that information, and a lot more stuff like that. But just remember that it's not that easy to become a data scientist. There's a lot of people who work very diligently at doing this. And one does not simply become a data scientist. So what is data science? I went to one of my favorite websites all time, Wikipedia, and asked it, what is data science? So Wikipedia defines data science as, data science is an interdisciplinary field of scientific methods, processes, algorithms, and systems to extract knowledge or insight from data in various forms. Well, I think you can summarize that quite shortly. It means you doing analytics, right? I think most people would agree that it involves doing analytics on data, gathering the data, cleaning it, and then performing analytics. That's the goal, is to perform analytics, to get insight, to get reports out for people who want to make any kind of decision. Why am I hearing myself twice? Maybe it's that. And I think a lot of scientists and friend of mine from the physics world would say that it's kind of the dark side of science, because no one really knows what happens under the hood. But kind of the first thing I'm going to do is I'm going to do data science on data science. So why not start by mining Wikipedia? I kind of already did that, and I'm just going to import that data into my session. Yes, evaluate everything. And I'm going to start playing around with that and asking questions like, what is data science? So we have this great function. A lot of what we do, we're right now in a Mathematica notebook, is build functions to make all this much easier and quicker. So one function we released about 2 months ago is called find textual answer. And what it does, it takes some question, in this case, what is data science? And it asks some corpus of text, in this case, the data science Wikipedia page, how do I answer that question with regards to that data? Now, I'm not going to go into what it uses. It uses like a multitude of methods, statistical methods, more advanced statistical methods like deep learning, and kind of a big layer of automation to pick the right type of algorithm to use in your case. But it does very cool things. And it gives answers. So in this case, it says that apparently from the Wikipedia page, data science is an independent discipline, which I think if people who practice a lot of data science, they realize that is kind of a chicken and egg thing. By the way, is this big enough for the crowd to see? Yeah. And I think that hints on the fact that data science is not very well described. So kind of continuing on this data science exploration, after I use this very, very high-level meta function to ask this very general question and I don't get the desired answer, I want to go one layer deeper than that. And I want to make a word cloud of all that data, and I want the size of the words, that's kind of how our function works, has to do with how many times that term is used in the corpus of text. In this case, we see that in the Wikipedia page for data science, data, unsurprisingly, is used a lot. Another thing that you use a lot is science, but not as much as data. And you can see kind of at the top here that statistical is used a lot, statistics is used a lot of use of the word term, which I think is kind of a red flag. Business, and we'll see in a second that in other scientists, business is not mentioned as much. So we see that it has to do with data, it has to do with the science of data, has to do with statistics, and has to do with business. But what are other ways to visualize that same data set, that same corpus of text, and kind of research it and look deeper? So in this case, I took the same data set, Data Science Wiki, it's a Wikipedia page for data science, and I broke it up into all the nouns. I basically extracted all the nouns out of it, and then I counted how many times each noun is mentioned in that data set, and then I sorted them low to high, and I selected everything that is above 5. So everything that is used above 5 times is going to appear, and then I listed that plot, and we see that we get kind of a nice plot here where data is used close to 80 times and science is used about 50 times, and then everything else is used less, which I think is kind of interesting. It's also interesting to see what kind of words are used. So term is used a lot, and like I said, that's kind of a red flag on the fact that you need to regurgitate the fact that it's a term. But data science, a lot of it is about comparison and modeling and looking at different data sets and seeing how they compare to each other. So the next step after this would be to do the same exact analysis on other major scientific disciplines and see how it looks. So that's what we did here. We're going to take the same, it's the exact same function we looked at. I kind of made it a little nicer so the picture's a little bigger. But it's making a table or kind of a list of 4 different Wikipedia pages. One is data science, another one is physics, then chemistry, and then biology. And let's just evaluate that and see what it brings out. And I think this is a genuinely interesting plot. Let me reduce my screen size so they all fit kind of nicely. And I really like this plot for a few different reasons. Like just looking at it, you see that physics, chemistry, and biology kind of have the same structure, right? There's 1 or 2 leading terms that are usually related to biology. Are there any biologists in the room? Unsurprisingly, no. But I think other scientists, we always laugh at biology that it's a science of memorization, and you see the first term is study. So apparently biologists need to study a lot. But you see that the following, it has kind of a very similar structure here. All 3 of them. The data science does not have that structure, which is, it doesn't necessarily indicate anything except the fact that maybe it's new, maybe it's formalized in different ways, maybe the people writing the Wikipedia pages are other people from different generation gathered from different textbooks and so on. But it is just an interesting view to see the difference kind of between the conventional sciences or the classical natural sciences of physics, biology, and chemistry and data science. Although data science is obviously applied inside all of them. And that's kind of a very easy way to look at different modes of data under the same superstructure, but seeing that they look differently. Any questions about this so far? About the validity of these plots? Great. So what are the current big challenges for business and the data science? The challenges that we see when we're brought into different teams to try and help them solve their issues. So the first and foremost one is their inability to handle different data types. There's a lot of different text coming in, there's a lot of different image data coming in, there's sometimes a lot of different numbers, and they could be structured in a lot of different ways. And that's a big issue, is how you bring everything in and make it, for example, numerical. How do you feature extract everything, or you translate between image data, textual data, numerical data, bring it into one standard form to one standard representation, and then use it later on. Another big issue is, and I think the two are kind of tied together, is that there's still insight cycle and an issue with reproducibility of results. So basically people are not able to rapidly use the same methods again and again on new data, on new areas, whether it has to do with the type of data or maybe it has to do with the way the databases are structured and allocated. Maybe there's some area of the company that no one really knows how to get data from, or it's in a totally different format and it doesn't necessarily work well with everything else. Another big thing is a lack of communication and feedback from the stakeholders, from the people actually trying to do something with the data, actually trying to get business insight. And I think there's a big differential between people like in this room that are trying to understand what to do with the data and between the people performing the data analytics. And there's a big separation there in what they want from each other. There's an inability to interface with the results. With that, there's a lot of different ways to look at it. One way I like to look at it is that you get a plot. At the end of the day, you as someone trying to, let's say, drive a marketing campaign, you get a plot of the data from your website. But it's not necessarily useful because you don't want the first plot you're looking at. You want to change a parameter. You want to look at it in a different way. And a lot of time, data is served in an uncustomized way. So it's served kind of in a very plain way. And there's not many good ways to deploy that information organizationally for everyone. One of the big reasons, it's not about setting up some web page that all the data are presented in. It's setting up different web pages for different groups that want to view the data in different ways. Because I'm sure the developers want to see it different than the marketing people, than the sales people, than the strategic people. And you need to create custom plots basically for each of them instead of having a central place where all your data is standardized and normalized and clean, and then you can go out and plot it for each group in the way that fits best for them, which we're kind of going to see. And that everybody wants answers, and they want them now, and they don't understand why it takes so long. I think that's another big issue that friends of mine working in this industry see a lot. So what is multi-paradigm data science? Multi-paradigm data science is an approach to doing data science that we formulated in Wolfram Research in the last 30 years, and we applied internally as well as externally for external companies. And it's data science that falls into these type of categories. So the first one, and the most important one, is it uses flexible pipelines built on arbitrary input. What I mean by that is that we use a combination of functions and methods that don't care really about what your input is, like whether it's a text or an image or a number. It could take anything and then translate into the same type of output again and again and again. And from different databases, from different sources, different files, and so on. Another thing is that it delivers better and faster insights. So because the pipeline is already set up and it's modular and you could just switch parts in it, the whole reproduction cycle is much faster. So after you set up a large pipeline for a certain website, for example, then different stakeholders in the company can come in and ask rapidly for different plots, different diagrams, different analytics, and get them very fast instead of a requirement to build a whole new pipeline and retrain everything. Another thing is to use meta-algorithms. So kind of a principle in our development and in the development of the Wolfram language, which is kind of the language we developed at Wolfram Research, is the use of meta-algorithms. So instead of an algorithm or a function doing one thing, it does 8 or 10 or 300 different things, and you don't really need to know what it does. What you need to do is that it takes the output, the input, and provides the right output. And maybe for textual data, it needs to use this type of algorithm, and for image data, it needs to use that type of algorithm, but you don't really care about that. What you care is that it provides you with the right output, and that's why the use of meta-algorithms is so important here. It's highly automated, so the selection of the algorithms, the selection of the type of feature extractor to use, which takes, for example, image data and turns it into numerical data, is automatic. So you don't need to worry about that, and you don't need to have some DevOps guy spend a month installing some libraries or some kind of programming for that specific type of task. It's scalable. So what you build in the small scale is immediately scalable for larger systems. And it's infused with real-world data, which we're going to talk about quite a bit in a second. And I think that's very important to understand how you relate the quantities and the different values in your system to the real world. So for example, let's say you get a request in from a client from England that's talking to you in pounds or in euros, and your team is working in the US, and you'd rather that automatically translate into US dollars with the current rate today. Maybe dates are very important, and we'll see dates in kind of an upcoming example. Maybe the area means something. So it's not just a zip code. It's not just a number. It's a zip code that has a meaning and has a geographical location. And I think that's hugely important, and it's something that's kind of overlooked widely, is what does the values and the quantities in the data actually mean? And the most important thing is that, of course, it delivers the right output to the right audience. So it's customized to the audience. So a person working, again, in the marketing department gets something different than a person working in operations or strategic management or any other department. And they always get that same report like they're used to getting it, whether it's an Excel spreadsheet like in accounting or in anything else, or a plot in some kind of visualization, or even maybe a program could be an output. And kind of these three things on the side here, these three nice looking graphs that are kind of based on fake data, well, except the graph analysis there because that's on a Wikipedia search, are basically kind of showing you that some groups want different data. Some only want histograms, others want more clustered analysis because they're trying to use that as a first stage. And they're all using the same type of normalized formulated data, which we're also going to use in a second. So a quick example, no code, kind of clean example. What we did here is we scraped the website for all the pipeline incidents of hazardous liquid spills in the US from 2010 till now. And if you look, the top left, so what's important to understand before I start is that this is all visualizing the exact same data set in different ways. So you see in the top left, what we have is basically the count, the amount of liquid spills for the entire US for each year and month. And you know, it's interesting to see different things, but it's not necessarily very insightful. But because we structured the data well and we know what days of the week everything was, we can also do this next plot, which is plots the entire age of all liquid spills from 2010 till now by the weekday. And that's already much more insightful because you see that for obvious reasons, Saturdays and Sundays have the least amount of liquid spills. I think that makes sense to everyone. But the first day of the week the first and second day of the week have many more liquid spills than the rest of the days of the week, which might say something about how people come to work on a Monday, working in trains or working in the trucks that move this, and maybe that's something that needs to be approached by policymakers. Then lastly, you see this, you see this monthly plot, which I don't think is immensely insightful. I do think it shows some kind of loop going on here, but it's kind of hard to decide. Yearly is kind of interesting because you see that until 2016 there was an increase in the amount of liquid spills. And then, by the way, this doesn't include 2018, I believe, right? It does not include 2018, so it's all full years. You see that there maybe have been some policy shift or some major spill that caused kind of a reduction of spills all over the US. The fifth plot here is just a pie chart of the type of spill. What was it? How hazardous was it? And the last chart, again, plotting the same data, because the data held the type of spill, where it happened, the date, and so on. Now we're plotting kind of a heat map, and let me, just look at that, is that you see that it plots all the different spills in the US, and the size of the circle relates to the amount of liquid spilled. I think most people would be unsurprised that Texas has a lot of spills, especially because there's a lot of stuff being moved in Texas, especially in the oil and gas industry. I was kind of surprised. I'm new to the Northeast. I just moved here 6 months ago, and I was kind of surprised that a lot of stuff is happening around the Northeast or kind of the Midwest with regards to liquid spills. And then I think that is, and correct me if I'm wrong, anyone know, is that Nebraska, right? That area of the pipelines? No? North Dakota. You see, I'm not from the US, so my geographic state is kind of limited. But again, same data, same exact. This is specifically an Excel spreadsheet, visualized in 6 different ways. Maybe 6 or 3 different departments would like to look at this data in 3 different ways and decide what to do next. So that's one example of multi-paradigm data science, at least from the visualization standpoint. So let's talk about a basic workflow in data science, and we're doing great on time. So the most basic workflow we can imagine in data science has 3 steps. The first step is about getting the data, importing it all to the same place. The second step is about processing and exploring that data. So It's about standardizing the data in the processing part and exploring the standardized data, which makes it easier to explore in the second part. The third part is deploying that data for all the different people that work for the company that want to access that data and look at it. So we'll do just an example of that. So I hope you guys, not a lot of coders in the cloud, I hope you'll still enjoy. So I went to this, not the curse of dimensionality, which is an interesting issue that we're going to track in a second. But I went to this website. It's called the Chicago Data Portal. It has tons of data about the city of Chicago. And I wanted to find a specific nice data set. This data set has to do with groceries. I think I wrote that wrong. So I'm not from the US and I'm dyslexic, so it's two double whammies on me. And I took this data set, the map of grocery stores in 2013 in Chicago. It's going to upload. We see it's a nice map of Chicago and the different grocery stores, and we can go in a little bit. It's interactive. I think it's based on Google Maps from what it seems, or at least that's the tile server they're using. And you see that we have this visualization of where the store is. But what if there's not that much more I can do with this now? I can probably view this in a few different ways, but I can't necessarily do a bunch of analytics on this data from their interface. But let's say I am a company that wants to open new grocery stores in Chicago, and I want to understand where I want to open the new grocery store. There's a bunch of other things I'd like to know, except where the grocery stores are right now. For example, the number of grocery stores in every zip code in Chicago would be an interesting question to see where should I place the next one, right? I can't do that through this interface. So what I need to do is I need to export it. Specifically, I want to export it as a CSV. And I've kind of cheated, and I did at least part of this beforehand in this notebook, which I'm going to open. Yes, here. So this is just exactly like if I right-clicked and said, copy link. This is that link. And let me import that link. We have this great function. It's called import, and I'll just show you import. And if I just grab this link, I put it here, and then I say elements. It shows me all the different things I can grab from that link. It also works on websites, on databases, on anything else. Again, meta super function. It works whether it's an HTTP address or it's a CSV file or whatever, and it shows you all the different elements. Specifically now, I decided the data is what I'm interested mostly in, not a summary or anything else. Although I wonder, I haven't actually looked at what does a summary here look like. So just a short summary of that data. It's just a CSV file. It's 0.1 megabytes. It has 507 rows, 17 columns. And now let's import that data. I just imported it into my session, and let's look at how it looks. So we see that we have, it says we have 17 columns. The first one is store name, the name of the store, license ID. That's less interesting right now. Zip code is interesting, right? We talked about zip codes. And then we also have kind of the location, which is kind of interesting, and the address, which is kind of interesting. And there's a bunch of different things I opened the wrong one. You can do with that data. So the first thing is you can look at the data in different forms. You can go and take this grocery data and say, let's look at how if I take all the rows of the 7th column, they're all just a list of zip codes, with the first one being zip code. How about instead of that, if I want to look at all, the names to see if any of them pop up. I'm surprised I don't see a lot of Whole Foods here. A lot of liquor stores in Chicago, if you've ever lived there, which is kind of interesting. I think it's because it's cold. But if I go to, let's say, the last column, so in our index, you can just, instead of last, you can write -1. I go and let's just take from the second row. So just we have one. We see that we have this geolocation. So it's a position on a 2-dimensional map of Earth. And I suddenly noticed the size of this document is not big enough for even me to look at it. So I bet you guys are having a hard time. Okay, better. But I know that parentheses is not the form in which this software package, specifically Mathematica, understands lists. So it needs to be in some other form. Specifically, it needs to be in curly brackets to be computed as a list. So this is the first part of what I'm doing in processing the data, is I need this to be in another form, to be standardized later. So there's all kinds of ways I can do this. One is to use an inbuilt function called string replace. The first argument of whatever string or whatever textual piece of text I'm trying to change up. The second argument is a list of rules I want to change. So let's say I want to say all the left parentheses going to left curly brackets, and all the right parentheses goes into right curly brackets. And that's the rules I want to do. And does that look like it should work? I'm missing something there. Perfect. Now it looks fine. I evaluate that, and you see that I get a list here of a list in the right format. Why is that useful? It's because I can take it to be an expression, which is expressions kind of how we formulate everything in this language. And then I can say I want it to be a geo position. That expression represents a geoposition, and then I want to plot that in a geographic plot. So I'm taking the geographic of the geoposition of this expression, and you see that it kind of gave me this point in Chicago, and it says that's where it is. Great. So it's in the right format for that. And now I learned a few things. So I learned how my data looks a little bit. I learned that some of my data needs to be transferred to another form for later computation and later analytics and later analysis. But then I know some other functions that I kind of want to use later on. So one thing I want to look at is the zip codes. So if I go to grocery data, and I believe zip codes is column number 7, 1, 2, 3, 4, 5, 6, 7. It is 7. And I want to take the second row, the 7th column, and I get this. It's a string. Or it's an expression, actually, just a number. I can check that easily if I asked its head. It's in some number. But I actually want that to be a number with meaning. Do you remember we talked about infusing real-world data into all these analytics? So we have this function called interpreter. Interpreter takes many different natural language objects. So something that's expressed as, just a string of a zip code, or maybe even other like location, dates. Dates it can take in a wide variety of forms. Basically, every way you can write a date, it can translate it into the proper way to write a date. And it'll turn that into an entity, a computable entity. And I'll show you what I mean in a second. So let's say I know it's going to be a zip code. And I know I want to input this specific zip code. And I want to input it as a string. That's why I'm adding those brackets. And then it comes out as this kind of weird, like yellow-looking thing. Now, what's interesting about that yellow-looking thing is now that it's an entity that exists in our system, and once it's in that form, there's a lot of stuff you can do. For example, you can ask, what's the properties of this entity? And now it's downloading kind of all the properties from the internet. I think zip codes don't have that many. Like a city like Boston would have 800 entities, for example, 800 properties. Like what is the median household income here? Different type of thing. What's the Gini index over this area? What's the total employment in that zip code? Stuff that is very interesting once you can have that in a computable form and you have real-world data kind of infused in. But out of all of these, we're mostly going to use their location, as you're going to see. But there's a bunch of different things here that are useful. There are companies that we do work for that are interested in new markets, and they want to know how did the weather affect sales, or what's the mean household income in a new market they're going to, or historically, how does the weather affect all the retail sales, which is all very interesting. And all could be used once it's in this form. So there's two major things I want to do. I want to reformat the data. I want to add kind of this entity or interpreter querying into all the zip codes. And I want to take all the locations and translate them into a proper entity look. And again, I cheated. Instead of boring you guys by watching me code all this, I just made a certain thing that does exactly that. There's nothing here that we don't do. It just takes this 17-column data set and makes it into a 4-column data set. And then it just adds all these different things, like it uses the interpreter in the exact same way we just used, and it uses the string replace in the exact same way we just used, and it does some other stuff. And I already did that because it takes some time to do that. So I'm just gonna, oh no, that was just very bad. It might be not that bad. Yes, I think it still should work. Let me just check, because I think, yeah, okay. So give it 1 second, it'll run. What I just did is I accidentally erased what I exported last time. Of course, it happens while you're live coding in front of other people. But it just takes it a second. It runs. It basically goes into each and every entry and matches and does a couple of sophisticated things. But it's done. Let's look at that again. Grocery data set. And we see it now. OK, nice. It's a nicely formulated data set. So it has the first row as a store name. And you can't really see, but if I kind of go deeper to how the underlying structure of this looks, it's kind of complicated. There's a bunch of things going on here. There's a bunch of different data structures that I put them in that just makes it much easier to do a bunch of computation that we're about to do in about a second. The other thing I kind of preloaded here is I went online and I searched for different server maps. So different, there's like Google Street View, there's Open Street View, there's Open MapQuest. Specifically here, there's one about like water maps or maps that look like they've been painted with a water brush. And I'm going to infuse that later on and show that you can use not just visualize your data in different ways, but kind of use different structures underneath your data to visualize the information very easily using different servers that supply you with different maps. So I also cheated and did that ahead of time instead of searching Wikipedia in front of everyone. So let's talk about how to visualize that data. So the first thing I'm going to plot is I'm just going to do a geolist plot of all the positions of all the grocery stores and put them on a map. And that's not very interesting, right? If you remember the original website we were at, did the exact same thing, right? Not very interesting. I didn't do anything useful. I just showed you we can also do that. In a cooler way, though, because it's programmatically. But now, what if I want to take that? So now my data is pretty well structured. It's normalized. I know how it works. And I want to use different tile servers. So I just add like a small function to start off with, and I just give it here an option saying GeoServer goes to I, and I'm about to say, I goes from, is basically all the tile servers. It's a list of tile servers. That's what I is. And now it's basically it'll plot that with this tile server, it'll plot it with another tile server, and you'll see it comes up to a couple of different maps. I'm a military man in my background, so this is pretty useful if you're trying to look at a new area to enter combat over, but it might be similar in other ways. This is the map I like the most. It's probably the least useful one, but it is the nicest one. And you see it's kind of this paintbrush, watercolor type thing. But you can, of course, apply it to a lot of different maps. There's 6 different ones here. There's hundreds of other servers online. Maybe you're interested in bike tracks. Maybe you're interested in major roads. Maybe you're interested in highways that are allocating resources that the truckers drive by, and you want to know where that is. These maps people have done this worldwide for everything, and you could just very easily access it and look at it different ways, and again, serve different people in the same company different plots about the same information. That's one way to look at the data. Another question we'd like to ask is, how many grocery stores are in every zip code? I think that's a very interesting question if you want to build a new retail store. Does anyone here work in the retail or in the grocery store business? Anyone here from a grocery store company? Yes, one. Is that interesting to know? Absolutely. Great. Yes. So let's say I just take this function that's called counts. It's pretty easy. And again, this is not something everybody in this room needs to know how to do, but you need to know that there's good systems to do this with instead of having someone do this for hours on end. And it might take a little more work in the front end of things. So I have this function called counts, and I'm just going to take the grocery data and put it into it. Specifically, grocery data, I think, is the zip code here is the 3rd column. Yeah, it's the 3rd column. I just cheated a little bit to remember. So I'm taking all the rows in the 3rd column, and I'm just Why do you not want to work? Oh, grocery data set. Excellent. So you see now I use this kind of function to look at how many grocery stores are in each zip code. And that only works because my data was well formulated ahead of time. But then again, this is just numbers of zip codes. It's not necessarily very, very helpful. I'd rather plot it, which is what I do here. And now I plot a heat map. So the more intense the color is, the more grocery stores are in that area. Interestingly enough, there's some issue with the underlying data set, which is why it doesn't come out here. But then even more interesting enough, that upper quadrant there is not a zip code in Chicago. And I had to look that up. Is that the airport or something? Or like I don't know why, but it's not a zip code in Chicago. I wonder where it's a zip code at, but it's not in Chicago. But you see that on the shoreline, kind of, there's usually less grocery stores, and you'll even see that more in a second. Maybe one great place for a grocery store is here, because we see everywhere around it there's a lot of grocery stores. But we see that it's very useful to know this information, and then sometimes we just want to plot both of them together. So we just plot 2, plot 1, and we just want to see them superimposed. So this is already, we're getting to something we couldn't do with the original map. We can see all the locations of the grocery stores. Again, they're kind of off the shoreline, which is interesting. Where they are in Chicago, and then the amount of grocery stores in that zip code. And that took us 15 minutes to do, maybe 10 minutes to do. It took us less once the data was formulated correctly, right? Standardizing data, building a big pipeline that works well on many different things. But then there's some other more advanced things you can do. And of course, by the way, I can do everything we did earlier with tile maps and different maps and road maps. We can do again with this pretty easily. But then there's more interesting stuff we can do. And here specifically, I do also a geolist plot. So I make a plot of all the points, but I'm adding a little tooltip that basically when I hover over it, it tells me the name of the grocery store. So, and that could give me any other information that I wanted. If I wanted the location, the revenue of that grocery store, if I was aware of it, how many grocery stores are in the zip code of the same grocery store, and so on, and I can start exploring this. And at this point, so we just, what's that? It's, I think this is a tweet. I think with the new Twitter stuff, you can fit this into a tweet. So with a tweet worth of code, we're able to make something that a person who's not a data scientist, who's just an analyst in the company, can start looking at and play around with, and is immediately extendable for the worldwide map. Like if you had all the data sets of all the grocery stores worldwide, I would just very easily take this and replace grocery store data with worldwide grocery store data right here and right there, and it all works the same worldwide for everything. So once you have your data well formalized to start off with, you can use it in a lot of very different ways. And I think a big goal is, like I said, to make interactive data that's manipulatable by people who are not coders in your company. And last and not least, there's a few other ways we'd like to export that data and share it around. So one thing is you can make a PNG, so just like an image file, and you have a nice image file here. You can share and email that around. Another thing is if you work on the Wolfram cloud, or you have a private installation of the Wolfram cloud, like many companies in the world are starting to have, you could just immediately deploy that final plot into the cloud and share it with other reports. We have a lot of financial companies that have been doing this for years, just because they're more kind of techie in their nature. And then you have this plot. It's a cloud object. I could add here a bunch of other things. It only sits online. I can send it to a million different people. We can talk about it while we're working on it, and we can attach anything else to it. But it's very easy to deploy it and just send it along. So that's a 3-step workflow. Now we're going to talk about the data science pipeline due to, I think I'm 12:30, right? I have 5 more minutes. This is actually kind of the core of the presentation, but because it was less Cody crowd, I'm not going to dive into it because this is like 45 minutes of just neural networks and blah, 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 and stuff like that I think are less interesting here. And I want to talk about how we imagine building data science pipelines, and I'll kind of finish with that in conclusions. We imagine data science pipelines when we build them for customers as complete adaptable workflows. So they're modular. You can add and replace parts like we did earlier. And they're full in what they do. So they go from basically from kind of scraping or importing to processing to modeling to reporting. They're systematic. They're agile. They're reproducible. You can use them again and again and again, and they show similar results. And they have standardized output. So again, you could take that output and reformat it in a bunch of different plots. And here's kind of a plot I love made from our training group, who are just amazing, and they have all this, by the way, is in free online courses at wolframu.com, or it's wolfram.wolframu.com, something like that. It's on our website. It's an 8-hour great course about data science, and they came up with this model of how data science looks and how does a pipeline look. So it starts with a question. Someone asks a question in the company, what do I need to know about this data? And then you have a huge ensemble of data, like all your sales data. Or another great example is, let's say you've logged all the possible emails ever coming in from customer support to your company that come into Department X, and you know that eventually all those emails go to different places, Department A, B, C. And once you have that data, you can make a pipeline that says, can classify that incoming email, it's going to X, but it should actually go to Department A first. And it sends it immediately there. That's just another example of the type of data you can use this with. And then the first stage is to wrangle all that data, so to bring it in one central place to perform analysis, to clean it up. We just did a little bit of cleaning in that example earlier. If you remember, we changed the brackets kind of. Then to explore the data, look at it in different ways, maybe count how many grocery stores are in a zip code. Then start the pre-processing and modeling. We didn't do a lot of modeling because that's kind of advanced, and I have a whole notebook here I'd be happy to share with whoever about modeling. But you apply a bunch of different models to it. Then you validate that model and you start telling your story, and you get into actionable insight. Actually, this great demo here that I'm very sad I'm not going to share takes kind of tons of ingredients and recipes, worldwide recipes, like 80,000 or so. And eventually, from like a huge database, an online database of recipes, it formulates a website that I can write in what ingredients I have in my cabinet, and it'll suggest what type of cuisine I should make, and then what are the foods I actually can make with that stuff, and maybe what I should buy. So that's actionable insight. It's kind of an interactive cloud-based website. It's very nice. So just to conclude, multi-paradigm data science allows you to, first and foremost, handle different types of data in a central way, explore and explain the data in different ways, deploy it everywhere in your company, and create long-term pipelines that you can reuse and reuse and reuse. And there's a lot more to learn about that in our website, mpdatascience.com, multiparadigmdatascience.com. And that's my email there, and it's going to be on this next slide as well. If anyone has any questions, I answer everything in email I ever get, and I would love to help you guys out solving your issues as well. Thank you. And we're right on time. Any questions? Anyone? They say a bad lecture is one that doesn't have any questions. Not even one.
I want to see the recipe.
You want to see the recipe? I'm telling you, it's if I go in.
It's lunchtime.
It is.
My wife's problem. She's like, I don't know what to make.
So just to see what I saved you guys. So all that is just coding. I wonder if I could just skip it all and go directly. Eventually I can skip it all and just go to the directly. I'll do that for you in a second. Any other questions? Except the recipes?
So the data set that you got was from Chicago City, right?
Yeah. So just this like City of Chicago, data.City of Chicago.
So basically similar data sets, how do you determine the format? Is it something that is
So the language I was working with, just an example, deals with that was a CSV. So we deal with about, let's see the length of that. With 200 different import formats, and they're all the underlying formats. You know how a lot of things are based on a CSV, but they're not called the CSV? So we kind of can interpret through that. So we have 200 different formats that we can input, so it doesn't really matter. It covers almost everything. And what you can't do, we can build a custom importer for.